Welcome to the second unit of AP Physics 1. We'll be looking at forces, and primarily Newton's laws of motion governed by forces. The simple mathematic expression for forces is a force is the mass of an object times its acceleration is a force. There will be two things that we'll be doing throughout this entire unit, and that's designing experiments that will collect data to determine the relationship between an object's inertial mass and its acceleration. And we'll define what inertial means. And then we'll also be drawing free body diagrams. All right, and we'll explain what that is in this particular unit. But the big key that we need to make sure we understand is that a force, a net force, or any forces are vectors. All right, they're all vectors, and so we have to add them like they are vectors because the direction matters. So when we look at a free body diagram, I'll abbreviate free body diagram in the text with capital F, B, and D. All right, free body diagram. Okay, so as we're looking at this free body diagram, a free body diagram is simply a drawing of the situation at hand, showing all the forces acting on that object. Okay, so we need to get in the habit immediately as soon as we read a problem, especially now moving into this Newton's laws, we have to get in the habit of drawing a free body diagram, because you can see just this one block here, just a simple sketch of a block has 4 different forces acting upon it. All right, and so let's go through what these forces mean and their abbreviation. So this is a free body diagram. The normal force, all right, is going to be equal and opposite to the downward force of gravity. So that will change depending on if there's an incline and those things, but it's always going to be in the opposite and equal and opposite to the direction of gravity. Okay. Friction, we'll talk about friction, but friction is simply the idea or the action against motion. All right, so friction is against motion, so it wants to slow things down and stop it from moving altogether. And then the applied force, APP, applied. Okay, so those are the 4 abbreviations that you'll see throughout this unit. Typically, we won't use this APP too much, we might just use an N, G, F, or maybe an A as their abbreviations, but this is the official abbreviations of these 4. But I typically use just a single letter. All right. As you can see down here is one of the most powerful equations in physics. Is kind of the little fun joke we like to play, is because the sum of all the forces divided the mass tells me acceleration, because we'll use this a lot as we move forward. All right, so adding all the forces together, all the vectors together, all right, divided by the mass is acceleration. Or I can rearrange the equation as the sum of all the forces, or a net force, equals mass times the acceleration. All right, so I just want to take a few moments to kind of break down that equation just a little bit further. You can see I've drawn a lot of arrows going certain directions. Just want to make sure we know what all the symbols means. All right, by now in math, you probably should know what that symbol means. All right, it's a Greek letter. All we use it for is the idea of sum. All right, meaning sum. That's all it means. All right, adding and subtracting those forces, using the Pythagorean theorem, whatever we need to do, adding all those forces together. All right. Acceleration is in the same direction as the force. As the net force, the acceleration is in the same direction. All right. So that's why I have all 3 of those rays. This is the geometrical way of writing a ray, or in geometry is how we write it. Okay, so I can break it down again into the x components and y components. So that's very, very crucial of what we do. All right, so if I look, just kind of give an example here. I'm looking over at this particular free body diagram again. All right, so the x direction, we're going to have the applied force minus the frictional force gives me my net force. Okay, pretty simple. Why is it subtracted? Is because this is in the opposite direction. And for the most part, the same thing with y. All right, so you have your force normal, little n there, minus your force of gravity. Gives me again my net force in the y. Now, this is not the total. So I can use this equation in one of the directions, not both. So net force should always be found. It should be for either the X or Y direction. I want to make sure I get that note in there as well. So in each system, there's going to be an X and Y. Keep them separate because they are. So a little bit more adding into it. This is kind of giving you a little bit more clarity and explanation. All right. When do I use these equations and when do I not? Because I'm adding 3 more right now. All right. So the only equations that I can use when I talk about the applied force, a normal force, or a tension. And we'll talk about tension in more detail later on. But tension is simply the force along a rope. Using a rope to transmit a force is all is a very simple definition. But those 3 forces are the only forces I can use is the force net equation. All right, F equals ma. Okay. Now, if I want to go further, if I want to start talking about friction, if I want to talk about weight or a spring, those things are entirely different, and I have to do a little. They have their own equation. So down here is how you calculate friction. You have your spring equation and your weight equation. All right. So all 3 of those cannot be used when I'm looking at the applied forces in the X and Y direction. They can only be used with friction, weight, and spring. Each of them have their own equation, and we'll talk more about them as that time comes. All right, so let's kind of get used to practicing drawing free body diagrams and the sum of our forces. An egg is in free fall from a nest in a tree. Neglect air resistance. Okay, so here we go. Let's get an oval here. Now it is in free fall, and we are neglecting air resistance. So I have 1 arrow to draw. That is simply the downward arrow of gravity, right? So this is the force of gravity. So what's the sum of this net force? It's also equal to the force of gravity because it's in free fall and we're neglecting air resistance. Air resistance is friction, so it would slow it down. But since we're neglecting it, I don't draw it in this, so there's only 1 force acting on this egg. All right, so let's talk about friction in all of its entirety. There's 2 types of friction. There are static friction and there's kinetic friction. All right, and I showed you that equation earlier. I said it equal to. Excuse me. I did give you the equal to, but here's the deal: friction of any kind, static or kinetic, can be equal to or less than my coefficient of friction. So that coefficient is the ratio between the 2 surfaces. So table book, wheel, rubber tire, asphalt, so on and so forth. All right, whatever that number would be, and there's a whole book, and you can Google and get this coefficient. These are going to be known coefficients times the normal force. All right, those 2 numbers multiplied together will be greater than or equal to the frictional force. If it is equal to, then I have static friction. Static friction means this is the friction that keeps objects from moving all together. Okay, there is no motion when you have static friction. Once you overcome the friction, where the force applied comes over it and overpowers this static friction, then you move to kinetic friction. Okay, kinetic friction, kinetic means motion. So it's the frictional of motion. So resisting the actual motion itself. So this is why what happens is when you start pushing a really heavy object, it's really tough as you're applying more pressure, more force. Then eventually when it breaks loose and starts moving for you, it suddenly gets a lot easier to pull that object or push it however it must be. Okay, so that's the kind of idea. So kinetic friction will always be less than static friction. There's no exception to that. There's no equal to. Okay, because if the kinetic friction is equal to static, then it would be static. So they have to be distinguished. Okay, and so I kind of gave you some examples there of how to rewrite those equations and see how it goes. Okay. And one thing to keep in mind is that kinetic friction will always be constant. So during the motion, this friction doesn't change. Okay, so the only thing that's going to change is my static friction until I hit this max and I overcome it. So important takeaways. Equal forces in opposite directions will equal 0 acceleration, not necessarily motion. The motion stopped. But equal forces in opposite directions mean there's no acceleration. There still could be motion. If I have unequal forces, I'm accelerating. This could be in the X or Y, but it could also be in both directions as well. Okay. If you have the same force and double the mass, well, that would equal half the acceleration, so that's an inverse relationship. All right, so between acceleration and mass, it's an inverse relationship. It's not a direct relationship. Okay. The free body diagrams is just a picture of the equation. It's all it's really doing. It's helping me picture what all the forces, where they're going, in what direction, and ultimately helps me decide what equation to use to find the sum of all the forces. All right. Mass here finally matters. Up to this point, when we calculate motion, we have not taken the mass of anything, and it doesn't matter. And we looked at it in lab, in which we found out that mass really doesn't matter when we're calculating acceleration. But since we were in a friction world, we couldn't remove all the friction. There was some discrepancy to that, but it was close enough to where you see that mass didn't play a part in velocity or acceleration, but forces it does. All right. And the two connecting pieces, the one connecting piece between the two components are X and Y. All right, those are the two connecting. I said that all wrong. The one connecting piece connecting the X and Y direction is friction. All right. So in motion of acceleration and velocity in the X and Y directions, time was our connecting piece, but here it will be friction. Friction will be our connecting piece. So good luck.